Good morning. Today we're going to review by talking about sparks in air, which is an interesting process. So let's talk about sparks. So the idea is this: you're going to shuffle across the floor, and as you reach out to touch the doorknob, you get a spark, and you go ouch because it hurts your finger. So what we want to talk about is this phenomenon of sparks. I'd like to show you a video of sparks. I hope I can get this to work right. So this device is called a Whims Hurst machine. And what it consists of is this thing is there's a plastic wheel, but it's got little metal plates, copper plates attached to it on both sides. And there are brushes that actually rub these copper plates as they go past. So you've got rubbing contact between two metal surfaces. And as you know, that kind of contact can actually lead to charge separation. These two jar-like things here are actually kind of function as a battery. The charge that's rubbed off gets stored in these. And so when the electric field, and these are connected to metal spheres on metal arms, so that when the electric field, the charge gets high enough and the electric field gets high enough between these two things, you get a spark actually. So let's look at some sparks here. So he's going to turn a crank to start it going. And here's a close-up with the spheres close together. Okay. So when those spheres were close together, the sparks happened very frequently, and when they were farther apart, it took longer for them to happen. So there are a number of questions that we need to answer about sparks. So one of them might be, why were there sparks when the spheres were, the charged spheres were close together? If this is actually charge moving between the spheres, how can charge move through the air? It's an insulator. Why does the spark stop? Or why does it last only a short time? Why is there light? Why did it make noise? Why did it make that crackling sound? And if we're going to think about you shuffling across the carpet to touch a doorknob, how does your finger get charged? So Seth, are you saying that everything has the potential to be a conductor?
Yes.
Okay, so presumably air can become a conductor, but how does that happen? So how can air become a conductor? So we have a lot of questions to answer here. So let's see what physics we can bring to bear to try to help us answer these questions. So first of all, a fact. You may or may not remember this, but what's called the critical electric field, the field required to ionize air, is about 3 times 10 to the 6th newtons per coulomb or volts per meter, and that's an empirical measurement that we just measure that and find out. The first thing we might want to look at is if air is an insulator, how can charges move through the air if air is an insulator? So let's take how can charge move through the air? Now, there are various models we might make, right? So if these are charged spheres and charge is transferred from one sphere to another, we might think that electrons jump across the gap between the spheres. We might think that protons jump across the gap. We might think that the air is ionized and electrons and positive ions drift in the gap. So what's your favorite model here? So we got about 2/3 voting for model 3 and 1/3 voting for model 1. Now either of those is actually a reasonable model. I mean, not a crazy model. I'm really delighted that nobody voted for model 2, because that means that we're not going to rip protons out of nuclei, which are held there very strongly by the strong force. So basically, more of you think 3 is likely, but 1/3 of you think 1 is likely. And so these are both plausible models that we need to consider. So either one is a possibility. So let's just look at model 1 for a minute. So model 1, electrons jump across the gap. So what would stop an electron from doing that? Well, the thing that would stop it from doing that is if it ran into something. So how far can an electron go before it runs into, so now what's it going to run into in air? Well, it's going to run into a nitrogen molecule or an oxygen molecule, presumably. So how far can an electron travel before colliding? Now, the gap between those spheres was on the order of, I don't know, 7 centimeters, I guess, actually, he said in the title slide, right? So can an electron travel 7 centimeters without colliding with something? And so what we need to do is estimate something called the mean, as in average, free path, which just means the distance something can travel in air before it collides. A particle can travel in air before it collides with an air molecule. Okay, so let's think about what this mean free path should depend on. If we want to know how far a particle like an electron could travel in air before it collides with an air molecule, what things should this mean free path actually depend on? Should it depend on the air density, the size of an air molecule, the speed of the particle, some combination of these things? Now think about the question. It's how far can something travel? So think about walking across a crowded room. Maybe how far can you go before you run into something or somebody? So the most popular answer is 5, but 4 was, so a third of the, so about 55% said 5, and about a third said 4. So some people think all 3 things, and some people think just A and B. Now, let's just think about this for a minute. So here's our, in 2D, here's our crowded room, and a room crowded with air molecules, and here's our particle that's trying to travel through here. Okay, if we have more air molecules, obviously you're not going to go as far before you run into something. So clearly air density is correct too. If these molecules are bigger, so if they were a lot bigger, then again, you're not going to be able to go as far before you hit one. So clearly the size of an air molecule matters. Does the speed of this moving particle actually matter? Well, if it travels really slowly, it's going to take it a long time to get to something it collides with. And if it travels fast, it's going to get there sooner. But did it go any farther? No, it actually went the same distance before colliding with another object. So therefore, particle speed is actually not one of the key things. That what's going to affect the mean free path is going to be the density of the air and the size of a molecule. So let's see if we can estimate the mean free path of something in air. So estimate which is the distance before colliding. So here's what we're going to do. We're going to say, let's figure out the volume of air in a room that's guaranteed to have one air molecule in it. So volume of air per molecule. And we could think of this as a big cube, but we could think of it as any shape container we want. So suppose we think of this volume as as a cylinder instead of a cube. And in fact, we think of it as kind of a thin cylinder here. So like this, that has some cross-sectional area A. And how big is this? What's the radius of this cylinder? Well, the cylinder is just big enough to, it's basically the radius of an air molecule, if you like. And in that case, we can guarantee that if we have some particle coming in here going that way, it will absolutely collide with this air molecule. So if we can figure out this volume of the air, and then we know the radius from, this is a molecule, we could actually figure out this distance d that would be an approximation, an estimate of the mean free path. So what's the volume of the cylinder? Well, we want this in cubic meters per molecule. So we know that at standard temperature and pressure, we have 22.4 liters per mole of gas. And we know that 1 mole is 6.02 times 10 to the 23rd molecules. And now we need to get this in SI units. So a liter is a cubic decimeter. A cube that's 1/10 of a meter on a side is a liter. So we have 0.1 meter cubed per liter. And let's see, we're going to end up with moles are going to cancel, liters are going to cancel, and we'll end up with cubic meters per molecule, which is right, and that comes out to about 3.7 times 10 to the negative 26th cubic meters per molecule. So now if this is the volume of this cylinder, we can actually estimate the length. We say the radius of a molecule, well, it's not a sphere, so it doesn't exactly have a radius, but let's say it's something like 1.5 times the diameter. I mean, we'll say it's around 1.5 times 10 to the minus 10th meters. Okay, so that's definitely an estimate here, but we're making estimates anyway. And so the volume of the cylinder is just the cross-sectional area, which is pi r squared, times this distance d that we actually want. And so d is going to be the volume over pi r squared, which is 3.7 times 10 to the negative 26th cubic meters divided by pi times 1.5 times 10 to the minus 10th meters quantity squared. And we get a number that's actually something like 5 times 10 to the minus 7th meters. And that is, in fact, the mean, our approximation to the mean free path of a particle in air. Well, that does not get us 7 centimeters. It gets us 10 to the minus 7th meters. So a free electron could only travel 10 to the minus 7th meters before colliding and coming to a stop. So therefore, electrons can't jump between the spheres. So we've just ruled out that model. So model 1 doesn't work. Okay, so let's consider model 2. Air somehow gets ionized. And ions are the mobile charges. Okay, that seems plausible. So we'd have a sphere that's positively charged here and a sphere that's negatively charged here on that Whims-Hurst machine. And we'd have two kinds of species in the air. We'd have, well, would you, okay, so the question is, would it be different in a vacuum? Could a spark happen in a vacuum? And the answer is, we don't see sparks in a vacuum. So that's another good way of, it's a good question, and it's a good way of thinking about what's going on here. So let's say we have a molecule, we'll say it's nitrogen, that's been ionized. So here's our N2 plus, and we've also got an electron here that came off it. And we've got a bunch of these. So we've got a whole lot of, well, these charged spheres certainly make an electric field. And of course, the electric field is in this region is going to be pointing that way. And so there are going to be forces on these ions. These positive ions are going to clearly move toward the negative sphere, and the electrons feel forces that make them move toward the positive sphere. And so, in fact, that would work, right? Then as long as we have ionized air, we sort of have a sea of mobile charges again, and no one mobile charge has to make it all the way across. All that has to happen is all the positive charges shift a little bit to the right, and all the negative charges shift a little bit to the left. And of course, some of them, the ones that are closest, are actually going to hit the surface of these things. So here we are with our charged positive sphere, and here comes an electron. And what's going to happen when this electron collides with the positive sphere? Well, of course, these two charges, the deficiency of the electron will merge into the metal, the deficiency of charge will disappear, and so it starts to neutralize it. And the same thing would be happening over here with different species. So we've got extra electrons here, but here comes an ionized molecule, and when it gets close enough, it can just pick up one of these electrons, and it also starts to get neutralized. And this explains why the spark would stop, because after enough of the charge has been neutralized, these spheres no longer have a big enough charge. The electric field is getting smaller. And eventually it's just too short, too small to sustain the the spark. So why does it, so we've answered the question, why does the spark only last a short time? And the answer is that these charged objects get neutralized due to the current flow. And so after a while, their charge just isn't big enough anymore, and we have to wait till the charge builds up again before we get another spark. Now, why is light given off? Well, we have two models here that we've learned in the past 2 semesters that help us explain why light is given off. So first of all, here are these charges in an electric field. We certainly have accelerated charges. And they can produce radiation. It's also the case that when this positive N2 plus captures an electron, it's going to a bound state, which is a lower energy state. And so, in fact, it could emit a photon. In our quantum mechanical model, or in the classical model, the electron gets accelerated a lot when it's really close to the N2 plus and it radiates. So both models work here, and we may be seeing both. We may be actually be seeing these accelerated charges here, maybe radiating, and then we're getting radiation from the recombination as well. The sound is basically what you're hearing. All that cracking noise is kind of like micro thunder, okay? The crack in a spark. And so these ions pick up a lot of energy, and the air is therefore getting warmer. And as they pick up kinetic energy, the air therefore locally expands suddenly, and we get a pressure wave coming off that. And that pressure wave hits your ear, and it's what the crack you're hearing. So the sound accompanies the sudden heating of the air as these energetic particles get energetic. So far this is making sense, but we don't know how the air can become ionized. So, but how can air become ionized? Well, one possibility is that, so this was model 2 here, so we'll call this model 2A. The electric field in the air is just strong enough to pull an electron off an atom. That doesn't sound impossible. But can we estimate the electric field required to pull? So let's estimate this field. So think for a minute. If I said to you, how big an electric field would you need to pull an electron off of an atom? Think how you do that. Just take a minute and think about it. Any ideas? Okay, well, let's think of a simple model of an atom. So here's our atom. Yes, yeah, great suggestions. The electric force has to be greater than the force between the proton and the electron. So, and the ionization energy of the molecule is going to come into it too. But for this, if it's just a field pulling on something, the force model seems like it would be really productive. So that's a great suggestion. So let's actually think about our really simple model of an atom. So here's our positive nucleus, and then we've got, in this Bohr model, we've got this electron traveling around it in an orbit. And even if it's not a circular orbit, but it's a spherical thing, it still has a radius. And this, I mean, this could be a hydrogen atom, or it could be that this positive thing is the nucleus and all the inner electrons, which still has a charge of plus E. And then this, so the system is this one electron here that's in this orbit. Let me draw it so it's over here. And so we've got this electric force by the nucleus. And so the force due to the applied field has to be at least equal and opposite to that force to pull that electron loose, right? And if we know the force, then we can get the field, because this is going to be the charge of the electron times the applied field, right? So we can get the magnitude of this field that we would need to do this. But this is a force that's actually fairly easy to calculate. Okay, so this force is just the charge of the electron times the electric field of the nucleus at the location of the electron, right? And we actually know this distance roughly. It's roughly 10 to the minus 10 meters. So we can actually calculate this. So the electric field of the nucleus is going to be equal to, we'll do magnitudes, 1 over 4 pi epsilon 0. The charge of the nucleus divided by r squared. And so that's going to be 1 over 4 pi epsilon 0 plus E, the nucleus and all the inner electrons here, over about 1 times 10 to the minus 10 meters squared. And this is 9 times 10 to the 9th, and this is 1.6 times 10 to the minus 19 coulombs. So and so we get an approximate value of 1.4 times 10 to the 11th volts per meter. At the location of this electron. Okay, that's a pretty big field. And remember that experimentally, the critical field was about 3 times 10 to the 6th volts per meter. So this is a factor of something like 10 to the 5th difference. So what do we do? do we just try to refine this model, or do we throw it out and say it's so far off that it's not, it couldn't be fixed by doing a better estimate of the distance? Or okay, so what we say is, if we're off by 100,000, a factor of 100,000, 10 to the fifth, this model just doesn't work. So we're going to throw this model away. So the electric field isn't just pulling electrons out of atoms. There has to be some other process going on. So let's think how else an atom could, a molecule could be ionized. So model 2B. Well, if we can't pull the electron off, maybe we could throw a boulder, throw a baseball at it and knock it out. Well, polarized is not charged, right? So polarizing the molecule is certainly going to polarize it. But we're not, in the end, a dipole is neutral, and so we're not really going to have charged particles that can conduct electricity. So polarization isn't quite good enough. But what if we shoot a really energetic particle at it? So knock out electron by colliding a fast particle with it. So model A, this was a force argument, and model B here we really are talking about energy. So we come back to Cole's suggestion of needing to think about the ionization energy of the molecule, because we're going to make an energy argument here. So let's say that we had, let's imagine that we had a free electron, for example. If we had one free electron, it feels the effect of an electric field. It gets a big change in momentum. It gets up to a high speed. It gets a lot of kinetic energy. And now when it hits one of these molecules, it could knock out an electron. So if we have, say, a free electron traveling at high speed, it hits a neutral molecule. And what happens is we actually knock an electron off. So there goes an electron, and now we're left with positive charge. So if we had just one free electron, we could ionize the air. So where would we get a free electron? Okay, so it's not just going to fall out of an atom, out of a molecule. So we have a need for a free electron. And a possibility here is that invaders from outer space could give us free electrons. Indeed, the space witch spider. These are a little different. So let's think about what we've got here. Here's the Earth. And here we've got atmosphere. So air. But there's a lot of stuff going on outside the Earth here. And the Earth is, in fact, continually bombarded with a variety of things, including extremely high energy protons. So very high energy protons. So a stream of extremely high energy protons come in and they get to the atmosphere. Doesn't have a top, but the beginnings of the atmosphere, right? And these protons, of course, are made of quarks. So protons are made of quarks. And they interact via the strong force. So they interact with the nuclei of air molecules. So interact with air molecule nuclei. And we get a whole zoo of interesting particles from that interaction. So we get positrons, we get protons, we get some neutrons, we get some pions, pi plus and pi minus things. We get electrons coming off. We get some neutrinos. We get some muons. We get both positively and negatively charged muons. One's a particle, one's an antiparticle. Now, many of these things aren't going to make it to Earth because they interact via the strong force. So all these things, strong force, don't make it to Earth. So they can't do much. These guys, though, neutrinos, they're neutral. They're not going to interact with the air at all, basically. So, but muons, actually, which are kind of like heavy electrons, are a really good candidate for coming down through the air, and they're charged. They don't interact, they're leptons, so they don't interact by the strong force, but they're charged, so they can actually ionize air as they pass. So what we'd actually get here is, so here's the air. Oops, let's make the air blue. Here's our muon, say it's a mu minus, coming down here, and it's just leaving a trail of ionization. So it's knocking off electrons and it's generating positive ions as it comes. Could be a mu plus. So the muons ionize the air. So is this possible? Well, the lifetime of a muon is about 2 microseconds, so 2 times 10 to the negative 6 seconds. After which, muons decay, so a mu minus makes an electron plus a neutrino plus an antineutrino, lower mu plus makes a positron plus a neutrino plus an antineutrino. And it only takes 2 times 10 to the minus 6 seconds. So the height of the atmosphere here is, let's say, significant density, about 40 kilometers. So 4 times 10 to the 4th meters. So the question is, how far can a muon travel before it decays? So how far can it travel? So let's see. Let's say it's traveling at the speed of light. It isn't, but so suppose if its speed was close to the speed of light, the distance it could travel would be the speed of light times the time, 2 times 10 to the minus 6 seconds. So this is 3 times 10 to the 8th meters per second. So it could travel about 600 meters, but we needed to go 4 times 10 to the 4th meters. So that doesn't look like it'll work, except can't go far enough.
Very necessary.
So if this muon is actually traveling at the speed of light, or close to the speed of light, what's going on with time for this muon? Time is passing more slowly. And in fact, time passes so slowly for this muon that it actually, plenty of muons actually do succeed in traveling from the top of the atmosphere down to the surface of the Earth, where they can ionize air. So remember, we talked about time passing more slowly for a particle traveling at high speed in a moving reference frame. The muon doesn't think all that much time has elapsed. It thinks it's taken much less than 2 microseconds to get to the Earth. So the muons actually arrive happily at the Earth, ionizing air for us. So what we saw when we talked about Alice and Bob and Einstein actually has a real application here in the real world. Now, there are much less romantic things that can happen too. Residual radioactivity near the Earth's surface in the Earth also can produce some particles that may succeed in ionizing air. But okay, we aren't getting Avogadro's number of muons down here. So is a small amount of ionization enough? Suppose we have one free electron. Is that enough? So is a small amount of ionization enough? What we actually can get here is a chain reaction. So let's start out with one nitrogen molecule and one free electron. And we have our free electron, we have our electric field here. And so the electron is going to be moving that way, and it collides with the nitrogen molecule. So this is our comic strip. Here's time 1. So at time 2, it ionizes it. So now what we've got here is here's our original molecule that's now ionized, and we have the electron that came off of here, and we also have our original electron. So now all of a sudden we've got 2 free electrons, and we still have this electric field. So now we have 2 free electrons that are going to pick up kinetic energy due to the work done by the electric field. And if they collide with 2 more air molecules, then what are we going to have? We're going to have 3 ionized molecules now. So we're going to have the original one. Let's draw this over here. The original one and 2 new ionized molecules. And now we've got 4 free electrons. So we've got 1, 2, 3, and our original free electron. And these are all traveling that way due to the electric field. And so now we can actually ionize 4 more molecules. And basically what we get is a chain reaction. So 1 free electron is enough to actually start this. We went from 1 free electron to 2 to 4. The next minute we're going to have 8. And so, there's a question in model 1, instead of the electrons jumping the gap, can they start to jump and then ionize the atoms when they collide with them? And the answer is any free electron can ionize an atom, but getting an electron out of the metal actually requires a fair amount of energy. We saw that when we were talking about the photoelectric effect, it was several eV, the ionization energy, to knock an electron out of a metal. And it's not real different from the energy for ionizing an atom, actually. So the argument about the electric field isn't big enough to pull an electron out of an atom, it's not big enough to pull an electron out of a metal either. Okay, so can we estimate the field? So we have one more thing to do. So this is what we're going to call this, model 2B. So can we estimate the electric field needed to get this chain reaction going? So estimate okay, and so here's what we're estimating, right? We want now so we want to know, can we put, we're doing the same thing. We're still talking about knocking an electron out, but now we're making an energy argument. So we say we need essentially the ionization energy, the amount of energy that we need to put in so that the electron can escape from the atom, right? So this energy to knock out an electron is got to be equal to the kinetic energy of the free electron. And so we need to know the potential difference over the mean free path, because that'll tell us the electric field required. So here's the scenario. Here's our electric field. This electron starts here and travels to there through a potential difference. So we have a a delta V here. And of course, the change in electric potential energy of the system is Q delta V, and the change in electric potential energy plus the change of kinetic energy is going to be 0. So we can get if we can figure out the amount of energy this electron needs to have, we can figure out the potential difference through which it had to travel, and therefore we can figure out the electric field. So the amount of energy required to knock out an electron. So here's basically our initial and final states. So here's the nucleus and the electron. That's our initial. And then the final state is the nucleus and the electron extremely far away. So this is final. And this distance is about 10 to the minus 10th meters, and this distance is infinity, or some approximation there too, right? And so we want the change in potential energy of the system, which is a minus E change in potential, which is a minus E times V final minus V initial. And this potential difference here that we're thinking about is taking the electron. What's the field we're worried about? We're worried about the field due to the nucleus here. So we're worried about the electric field due to this nucleus as we're pulling this electron away, right? So that's the potential difference. And so the potential difference is going to be minus E dot dl from initial to final. And that's going to be, what is it? Well, we're starting at a distance r, which is the atomic radius, and we're going to infinity. And the field is the field of the nucleus, so that's a 1 over 4 pi epsilon nucleus plus inner electrons, or we can, so plus E over distance squared, we'll just call it x, or r squared, dr. And we actually know that integral, right? We've already done it. So what that's going to give us is a 1 over 4 pi epsilon 0 E times 1 over infinity minus a 1 over r. And this, of course, is going to be 0. 1 over infinity is 0. So we have, so let's just worry about magnitudes here for a minute. So we've got 9 times 10 to the 9th Newton meters squared per Coulomb squared times 1.6 times 10 to the minus 19 coulombs divided by 1 times 10 to the minus 10 meters. And we get about 14.4 volts. Which is, as you remember, maybe from last semester, about the not unrelated to the potential difference to ionize a hydrogen atom. So the change in potential energy is then going to be E delta V. So that's, we multiply this by minus E, and so we're going to get we're going to get a 1.6 times 10 to the minus 19 coulombs times, this actually comes out to a negative number if we do it right. So it's going to come out to about 2.3 times 10 to the negative 18 joules. So the kinetic energy of the electron must be about 2.3 times 10 to the negative 18 joules, or greater than or equal to, say. So can we do this in one mean-free path? So free electron starts from rest. Travels one mean free path. Does it have enough energy? So here's our system. Here's our electron and the electric field due to these charged spheres. And the change in kinetic energy plus the change in potential energy, so it includes the charged spheres. So we have delta K plus delta U is 0. So K final minus 0 plus a minus E delta V gives us 0. So K final is going to be equal to a minus E delta V here. So the potential difference that we need is just going to be the final kinetic energy divided by the charge on the electron, which is equal to 2.3 times 10 to the minus 18 joules divided by 1.6 times 10 to the minus 19 coulombs, which is equal to about 14.4 volts. Not a big surprise. But this potential energy is going to be equal to the applied electric field, this electric field that's causing the spark, times the distance, okay? So we can solve for this field that we need to make this happen. It's going to be this potential difference divided by D, so 14.4 volts divided by what we estimated for the mean free path, 5 times 10 to the minus 7 meters. And that gives us an approximate value of about 2.9 times 10 to the 7th volts per meter through this energy argument. Now remember that the observed critical field is about 3 times 10 to the 6th volts per meter, so we're off by a factor of about 10. So how about this model? Is this model reasonable? Well, our estimate before, so that we're saying that the required field, we're estimating the required field is about 3 times 10 to the 10th to 7th, and really we measure 2 times 10 to the 7th. So our estimate is too high. We need too big a field. Now last time we threw out a model because we got 10 to the 11th volts per meter instead of 10 to the 6th, and we said, well, that's crazy. But here we're off by 10. That's actually pretty good for what for all the approximations we've made here. I mean, think about all the things we've just kind of thrown in there: the radius of an atom, estimated mean free path. So not bad. Well, here we're actually making estimates, and it's actually pretty tough to write an online homework problem that lets you that asks you for an estimate, because it's actually hard to convince it to judge estimates reasonably. So unfortunately, in homework problems, you have to be off by less than 2%. But this process of estimation is actually kind of an interesting one. So for estimates, this actually isn't bad. But it also has, there's also some teeth in this model, because having done this, we can now test this model empirically. Because remember that this model said that a key feature of this model was the fact that we were estimating the mean free path. And to get that estimate of mean free path, we used the density of air, the 22.4 liters per mole at STP. So we can do experiments, and we say, well, the mean free path is proportional to the air density. So what should happen if the air density increases? How should this affect the electric field needed to make a spark? And we can actually make that measurement. So if we increase the air density, should the critical field increase, decrease, or stay the same? So remember our argument. The electron travels one mean free path, having under the influence of that electric field, and in that time, in that distance, it has to get enough energy to knock the electron out. Okay, so what you said, the majority said that the critical field should decrease. Now let's think about whether that can be right or not according to our model. If we have low density, then our putative free electron gets to travel, has this far to gain enough energy to knock an electron out of another atom. If we have high density, the electron only gets to go maybe that far. So if it's going to get the same amount of energy, it has to have felt a much bigger force. It has to, its momentum, it has to get that whole momentum change in that distance instead of a longer distance. So in fact, you're going to need a bigger electric field. And likewise, if you go up on top of Mount Everest, where the air is very thin, the electric field required should actually decrease. And these are easy experiments to do, and it turns out to be the case that in fact, if you increase the density of air, you need a bigger critical field, bigger electric field to get a spark. If you decrease the density, you need a smaller field. So that's not a proof, but it's actually evidence that our model makes sense. So the one thing we didn't talk about, which we should just talk about briefly, is how does this work for your finger when you're shuffling across the floor to touch a doorknob? Because presumably you've got insulating shoes. So your finger presumably isn't actually getting charged. So here's the carpet. Well, any charges that we get are probably going to be on the soles of your feet. Let's say they're the soles of your shoes. Let's say they're they're positive, so the carpet's negative. But now all that ionic solution inside you can actually polarize. And so presumably what we're getting is chloride ions in your toes, sort of concentrating in your toes, and we've got some sodium ions concentrating in your fingers. So you're not charged, but you are polarized. And what you can do, therefore, is actually polarize the doorknob and end up with a big enough electric field to start a spark. So we see here that what we were able to do is to actually rule out some models and to affirm others with these physical arguments involving E and M that you know and love. So that's it. I want to thank you for being awesome this semester. In fact, this whole year, it's been a unusual and difficult year, and you've hung in there. You've been engaged. You've been funny. You've thought hard. So you've been great. Thanks for a great year. So type something in chat so I know you were here. What was interesting today? So the ions in your bloodstream certainly are going to polarize, and the molecules in your tissues will polarize for sure, right? So lots of polarization, but there are a lot of ions in your blood. You can put your finger in those sparks, but you touch one of those things, it's going to hurt. I don't think that much polarization is going to hurt you, no. You still have a lot of ions in every place.